from setting up the problem a lot of times. Actually, the calculus is not necessarily the big part of this. So homework 6 will be, since we're going to do a quiz tomorrow, homework 6 will be due on Friday. So all right. Now, I do have a note sheet for you. Okay. And by that I just mean here are the examples I'd like to look at. Some of them, maybe not. I don't know that we'll have time to go through every example in this in class. All right, so we'll do a bunch of these. They all have. I'll just give this disclaimer right now. There's just no way I can expose you to every kind of optimization problem that exists, because there are just so many. I mean, they'll have maybe a geometric flavor like this, or maybe they'll have a more analytic geometry type thing, or do something on the coordinate plane. We'll do one of those before you leave today too. Optimization problems are just basically anything that you're looking to optimize. And by optimize, I mean find the largest or the smallest value of that thing. When we're only doing like kind of one variable optimization. But obviously optimization is a super important idea in the real world. We're always looking for optimal conditions. So why don't you read and digest this question? I'd like to give you maybe a chance to just kind of set it up if you can by yourself. Again, that's where the heavy lifting has to happen. The calculus, I think you'll find, is just really somewhat trivial on this. Keep in mind that this, because it's along the side of the barn, I don't know if this is clear from the question, you don't need a fourth side of fencing. If that makes sense.
Oh.
Okay. Oh. So maybe that's not clear from the question. So sorry if that's not clear. I don't know how you want to draw the picture. Here's the barn. The barn is, sure, it's however long you need it to be. It could be at least 40 feet, sure. How about, let's say that it's at least 40 feet long. It's a huge barn. Okay. Here's the barn. We'll draw the rest of it. And then the fence will be built like this, right? So it'll be rectangular, right? But you only need to build 3 segments of lengths of fence. Okay, so now with that clearly in mind, keep going. And open the discussion at your table to make sure that
we got a solver to a and L times W.
We can consider whether what happens if, like, let's say the width is 0.
You might start by like naming some things, right? Give some letters to these things. If you haven't done that already, so you have a common language at your table as you talk. You may want to write down anything you know. You have a formula for the area. How does the length of fencing relate to that?
Wait, hold up. Yeah, not rectangle. B is the side of parallel. You could write the perimeter as a function of your here too. Because a square, because you can make a square that will have a perimeter. No, it won't. How does it instead of a circle? Okay. If we have a 6 16 square feet. So 2 by 8 4
Wait, no, never mind.
plus 16 is 19. It's not the same as
Okay.
as 16. So yeah, those are not the same.
Yeah, I think that's kind of critical.
Can I see how big? Yeah, like plugged in 11.
Can someone give me some letters they really like? What letters do you want me to use?
L and W.
For this blank here, what do we call that? The short sides. What do you call them? Huh? W or width? Okay. Alright, I'm going to go with W, and this is like length. Okay, yeah. Depends on how you orient your diagram. Alright, cool. And then I think I saw lots of people writing down A equals W times L. You wrote that down, maybe. And you also wrote down that 2W plus L is equal to 40. I saw lots of people writing those two things down. Okay, and then, so good. I think this is a great place to start. You want to like name some variables that maybe make sense to you. I saw a lot of people using A and B, X and Y. Great choices, all very good choices. Just want to affirm you, okay? And those are the critical pieces of information. I mean, we really definitely have mined the problem for every piece of information that we could possibly have. I think it's all there. Then what? You want to have like a way in on this a little bit? Amy wants this one. She's hungry for doing this one. Go ahead. I mean, give us some way in.
So, what I did was, what the equation for like the area would be a WL. So then,
Correct.
But L equals negative 2W plus 40. So can we
Whoa. Slow down, Professor. Okay. Hold up. What'd you say?
L equals negative 2W plus 40.
Oh, I'm with you now. L is also known as, so maybe there's really like only one variable in the problem, W. Right, we got W and we got 40 minus 2W. Do you see what she's doing there? She's like, the only thing this equation was good for was like telling me what L is in terms of W. And she's gonna like plug it in over here. By the way, why didn't you do, I mean, you could have also maybe solved for W in this, L in this equation and like put it down here or something. I don't know, but it doesn't matter, I guess, okay. W times 40 minus 2W. Does that look good? Is that what you did?
And then I graphed it, and I found the maximum because it's quadratic.
Okay.
And then the
I think I have other ways of finding the maximum without a calculator too. Okay. How do you find the maximum? By the way, this is now a function. Before I wouldn't have been able to write A of W, right? Because it's A of like, A is a function of two variables originally. But now A is a function of only one variable. It's A of W, you could call it, is 40W minus 2W squared. Okay, so then the question is, divorce this from the context completely, and then let me ask you this question. What is the maximum of this equation? No calculator, go. I think you have some tools in your tool belt to find the maximum of a function. How does that go? Yeah, oh, okay, all right, that's right, it's calculus class. What did you say, Christine? Yeah, so maybe we think about what the derivative is, and it's, again, the calculus piece today is not necessarily the hard part, it's all this other stuff, right? Then because here I don't need to ask someone. I think we all, at this point, can safely take a few power rule on that. And then what? The derivative is fun, but why was it important? What's going on there? Why do we want to identify that? Yeah, and this is nicely differentiable. The only time when this will possibly have a critical value here that we care about that could maybe be a max or a min is when this is 0. So that's pretty quick to solve. In fact, you can just do it by inspection. W equals 10. Great. 10. What? Something. 10 feet. Okay. By the way, before we actually consider that to be a maximum, we better also just double check and make sure that it is in fact a maximum, right? So there are two ways you could do that. You could make a little number line, right? And put put 10 on it, and then test this function to the left and right. Or, again, we're all about the second derivative test too. What's the second derivative? It's -4. It's always negative, isn't it? Or you could just know that it's a parabola too, I guess. But one way or another, let's just somehow, please, just check that that is in fact the maximum, okay? So since the second derivative is negative for all values, it's certainly negative at 10, right? So that means it's concave down. That means this is a maximum. Yeah.
So like, say I did it wrong, or like calculus. So what if I just did negative b over 2a?
Yeah. That on this particular problem that would work. But I guess couldn't a man ask you why negative b over 2a works though? Couldn't a woman could probably ask you that too? Actually, that's true. Couldn't someone come to you and be like, okay, but that's magic from like on high. Where'd you get that? Like, what is that? And then you'd be like, oh, well, let me take the derivative of a x squared plus bx plus c for you and show you that you know, we can actually, it's 2a x plus b equals 0. And when you solve for x, you get negative b over 2a using calculus, right? I'm just saying maybe you are using calculus, you didn't know it, right? Work that out, okay. For any general quadratic, find that x equals negative b over 2a is the maximum. Okay. Good. We didn't actually answer the question though, did we? What's the answer? By the way, what is L? L is 20? All right. By the way, so these questions, make sure you're really careful about what the question asks. Sometimes it'll say something like, what are the dimensions that maximize the area? In which case the answer is 10 by 20, right? Sometimes it'll ask you, what is the maximum area, like it did here, in which case those are interesting, but the actual answer is 200 feet squared. Make sure you get the units on there. Is that cool? See how this works? Nice, easy example with a quadratic to start us off. Beautiful. Okay. So that's how these feel. I have like this easy 3-step process for you to kind of just highlight what we just did, in fact, right? I think a lot of people, just right at the way at the beginning, are thinking, okay, I have like an equation for the perimeter, I have an equation for the area, well, which one am I going to end up taking the derivative of? And they're like, get like kind of lost in the weeds. Make sure that in the end, the thing you're maximizing is the thing you're trying to take the derivative of, right? If we're looking for the maximum area in a certain situation, then you better have like a function that gives the area, right? And that's the thing, and hopefully only has one independent variable, you know, like we did, a of w. That's the thing. Now we're in a situation finally that we're like ready to do our calculus. But I think a lot of people get like we have this like box problem that has like cost involved too, and then you're like, oh, is it surface area or volume? No, it's cost. Which thing? Right. If we're minimizing cost, well then you better have a cost equation that you're going to take the derivative of. So don't get lost in all that because there's sometimes like a bunch of equations that are floating around. So make that clear in your mind before you do anything else. What is it that you're optimizing? And are you looking for a min or a max of that thing? And then this is what we did in the last one too, right? Write the equation in terms of only one variable, independent variable. You saw that just happen in a second ago. Notice that all of this so far is just free calculus, right? This is really not any calculus. Then finally, on number 3, you actually find the maximum using calculus techniques, right? Yeah.
So after we take the maximum, do we plug it back in to find the other, to find the other sides?
Is that like on the last problem, you mean?
Yeah.
Yeah, so we found that the W that yields the maximum area is 10 feet. So if we desire to have the length, we could get it because we have a formula, L equals whatever it was, 40 minus 2W. You could plug your W in and get the length. You actually didn't need to do that on the last problem, though. You could just go up. We actually have a formula for area right here in terms of just W. So you would never, now keep in mind that in doing that, you actually are stealthily calculating the length along the way. But this is technically, yeah, you just need to plug 10 into your area formula, right? Which only involves W. So there are a couple ways to think about it, but yeah, make sure, I should have maybe added that as a 4th step. Make sure you actually answer what was asked, too, with units and give the actual answer to whatever the question was, even if you've done all the great work you've done. Sure. Let's do jump to number 4. Just because I think it's interesting and a little bit different in flavor than the last one. So. Sounds so innocent, right? But first of all, number 4 says, how close does a semicircle y equals 16, the square root of 16 minus x squared? You realize before we even go any further, you realize what that guy, it's kind of assumed that we have a picture of that already in our minds, but maybe you need to generate it, or the first thing you might want to do is just picture that in your mind. What does that look like? Radius 4, top half of the circle centered the origin of radius 4, right? So you graph that in your mind or on your paper. And then we have this point 1 root 3, which, let's just be clear, is not on that curve. Do you agree? Okay. Where is it, by the way, like, if you were to draw that picture? It's inside of it, actually, right? So, so maybe I do, just for the sake of building intuition, I want to maybe like think about what it is I even mean by how close does the curve come to the point. Is it okay if I go off this slide? Okay. So yeah, so I might actually draw this a little over here. Okay, so that point is, where is it? 1 root 3. This is 4. 1, 2, 3, 4. I just want to have some sense of 3, 4. 1, 2, 3, 4. So 1 comma root 3 is like right there somewhere, right? So what do you think? How close do you think it comes? And by that I mean, like, that's kind of 2 questions in one, isn't it? It's kind of like, where do we have to be to be as close as possible? First of all, that is, consider the set of all points along this curve. Where are we the closest? I think it's definitely not like over here, right? We're kind of far away. I think I can think of closer points. They're over here, maybe. But maybe it's somewhere in here. How would we actually do this? I mean, for any given point, how do we know, like, what its distance is away from the point we have? Well, can we, like, compute that distance for a given point? I don't know. Yeah, John?
Well, it's a circle, right? It's half the circle, right? So the closest distance from the circle to the point beyond it, the radius where the point's touching the radius.
Point is touching the radius.
Oh, I see what you're saying.
I'm struggling to see what you mean. Which point and
No,
which
no,
radius?
it's draw a radius from the outside where the touches the point. That should be the closest.
So, like, say I was at this point.
Alright.
So, describe what I need to do. Draw a radius from here.
From the origin, draw through the point.
Yeah, draw through the point.
You want me to do that?
No, the original point.
Yeah.
Oh, 1.
You just want a line through the origin.
I know. I'm just trying to figure out what radius, what your word radius meant to me. I don't know. I think I drew that already, right? I mean, this is the set of points we want to think about. I mean, we want to think about which of these is the closest. How do we compute their distance? I don't. Maybe we just.
So I think what John is saying is if you draw a radius from 0, 0 to a point on the semicircle, and the radius has the point 1 root 3 on it, on the radius,
Mhm.
then
Then that must be the closest point.
so that makes sense.
I guess we'll find out. In a second here. I don't know that I necessarily. I don't know if I agree with that necessarily. I'm just thinking visually about it. Yeah, will that be on the radius? Let me think about that. What about a point? What if we did this with a point outside instead, like at 1 root 3? How would that work?
That's a good question.
I mean, I'd like to do this for any point. There's nothing special about 1 root 3. So, all right. So, is there a way to calculate the distance?
Yes.
For a generic point on the curve here. And by a generic point, I mean like pick an x value between -4 and 4, and tell me what the distance would be, right? Because if I have a distance function in my possession, then maybe I can find its minimum value. Yes? I'm looking for like the segment I drew that produces the minimum distance, right? So can I come up with a function that just gives me the distance for any point I like along that curve, x equals -4 all the way up to 4. And then I can just consider all those values at once and think which one gives me the lowest. Yeah.
Oh, actually, never mind.
Wait, have we come up with the equation, or are we still like thinking?
Yeah, no, we haven't yet.
Oh,
Do you have?
can I present?
You want to present an option? Okay.
How about we draw a line y equals √3, and then we do the Pythagorean theorem. You know,
Yeah, you mean to like actually compute that the distance?
Yeah.
Yeah, there is actually a distance formula that you learned at one point, and it is just really the Pythagorean theorem, right? Do you remember how it goes? I mean, it's really just the Pythagorean theorem in the way that you just said. It's the square root of some stuff. Yeah. Yeah, I'll write it that way first. It's now if one of the points is 1 comma √3, just for the time being, let's make the other point x comma y, I guess, just for now, but I might want to come back and pick that again in a second. So what is the distance between 1 √3 and xy? Give it to me like that. How would that go? X minus 1 squared plus, and then keep in mind what we've just done there. Remember, the picture is that like this is one side of the triangle, one leg of the right triangle is like the difference in the x coordinates of those 2 points, and this is the difference in the y coordinates, which gives us like the other side length. And this, by doing this using the Pythagorean theorem, we're calculating the third side in between the hypotenuse. Right? So I just want to make sure you remember where the distance formula comes from and why it makes sense. Great, but y has another name, doesn't it?
Oh.
What's that? Yeah.
that was only.
So, and this is kind of the critical piece here, right? We now have it in terms of one variable. Right? So we're going to find the minimum value of d, aren't we? Like we're going to find the minimum value of this function. Now there is a hint here that might help us a little bit, too. Okay. It would be nice if we could make this conclusion, and I think I can convince you that it's true, unless Judah wants to do it. Go ahead.
Oh, we know x is positive because it's the slowest positive, and it's 1 for 1 if you cut it off past x.
That's like a very, very high level explanation, and I like it. Okay, so yeah, there's something about the fact that we can square this, I guess. I was just going to convince you with like a picture, but you have a much more sophisticated read on it. I like that. Okay, so there it is. If you square both sides, and I have this graph for us on the calculator. Here's in y1, I actually have the cursor is blinking over top of it, but I promise this is the square root of, it's all the stuff we just typed in, right? Except it's reversed, but whatever, doesn't matter. So this is in here. This is this graph right here. You see it? The second thing I graphed is this function squared, which is of course this one. So this one is up here, and it's certainly true that these will have the same minimum value. You could also think about like, since again, I think it matters that it's positive maybe, but if you think of, we were to like, I don't know, collect data on all the distances you guys travel from here to school each day or something like that, and you were to all write them down, and we were to try and find the lowest one in the room. Wouldn't that person be the same person as if we squared them all and asked which one would be the lowest, right? I think you'd still be the lowest, even though your squared value would be bigger than your unsquared value, of course, but unless, like I said, unless we have negative values, and we don't. So I think if we're good on that, if we acknowledge that that's going to be true, then I think we're good. All right, so then now you're just taking the derivative of this expression and setting it equal to 0. Right? The calculus can begin now, okay? And by the way, what do you think the answer is from the picture over here? Yeah, how close does the semicircle come? Now, x equals 2 this is a little bit inconvenient actually, I feel bad. X equals 2, it looks like, is the answer you'll get here for the x value. The x value at which you need to be in order to minimize the distance, so I guess that one right there, approximately, what is that distance? You might actually be able to pick that off from the lower graph too. Unfortunately, it also happens to be 2, which is inconvenient because like you might be like, oh, I'm done, x equals 2. But you still do need to go back and compute it in the original equation. And you'll find that it equals 2 as well. So this is a little bit of work in here, but I believe in you, okay? But I will just tell you right now that the answer you will get is 2 there. For the minimum distance, which is what was asked. Yeah. An algebra question? Okay.
So like if I'm like if I like distributed the square and I can't get rid of
No, you have to FOIL that out, right? You have to, right, yeah. Both of these things you need to multiply out, which means there's still going to be a square root in there, right? Sadly. Yeah. I mean, a lot of nice stuff happens and goes away and combines, that's good, but in the end, it's still not really that nice looking. All right, I don't want to like dwell on that too much. I mean, you can wrestle with the algebra, but it'll take us a few minutes to actually resolve that. I'm not trying to like short you of that, but doing the calculus there and the algebra is a chore that you can do later. Okay. Can we at least maybe get a little bit of an inroad on one like this? I'd love to have one that involves like an angle. I think that's cool. So let's throw this one up here too, and see if we can at least get it. Again, just set up at least. This is not quite as complicated a discussion as the last one, I don't think. Two sides of a triangle have lengths A and B. And theta. Okay, so some triangle A, B, theta. And the angle between them is theta. What value of theta will maximize that triangle's area? It doesn't seem like we have a lot to go on, but so I guess at some point we'll need an area equation for this triangle, won't we? What are you muttering over there, Babesh? You want to share with the class? There's like an actual formula that gives us these things, gives us the area. Can you say it again? 1/2. All right, it's not necessarily required that you would remember that necessarily. It's very quick to rederive that if you aren't Babesh and you don't happen to remember that, okay? What's the area of a triangle? It's 1/2 base times height. So it's 1/2 base times height, and what is h? Can you convince yourself that it's really just a times the sine of the angle? All right, so even if you didn't have that formula, quote unquote, memorized, I think you could still do this with 1/2 b h, right? Okay, so in fact, maybe we should write that up here just to remind you that that's a fine way to do it, and then you maybe realize that this is true. Okay, so great. I mean, that's like the big part of that problem that makes sense, right? All right. So that gets you started at least on these. We'll spend some more time talking about these. In fact, this set of problems on Friday, just more of the same on Friday. You don't need to work